This video is the supplementary material to our paper. We propose a novel partially decoupled motion planning method for the aerial pick-and-place task. Compared to the state-of-the-art approaches, the proposed one has two novel features. First, it does not suffer from increased computation in high-dimensional configuration spaces. Second, collision avoidance for the delta arm is achieved through an iterative approach based on a pinhole mapping method. The aerial manipulator considered in this paper consists of a quadcopter base and a delta arm. The end effector used in this paper is a gripper and it is mounted on the end of the delta arm. The geometric feasibility constraints are proposed to ensure the trajectories of the quadcopter base and the end effector satisfy the geometry of the aerial manipulator. The constraints can be calculated from a revised workspace. By using these constraints, we can plan the trajectories of the quadcopter and the end effector, respectively. The overall system of the aerial manipulator is decomposed into three components. The first component is the motion planning of the quadcopter base. Compared to the existing methods for standard quadcopters, the proposed method has two novelties. First, the feasible grasping position is calculated for manipulating the object. Second, the flight corridor is divided into two stages, moving and manipulation stages. The second component is the motion planning of the delta arm. It is solved by an iterative approach based on the GJK method and a pinhole mapping method. Compared with the existing methods, the proposed method requests lower computational power since the collision avoidance is achieved by an iterative approach in Cartesian space. The third component is the controllers of the aerial manipulator. We validate the effectiveness of the proposed method in the collision avoidance task. Without the collision avoidance method, the length of the collision area is 0.026 meters. With the proposed collision avoidance method, the resulting trajectory is collision-free. The goal of the aerial retrieval experiment is to retrieve an object by the aerial manipulator. The span time of the experiment is 58 seconds. The computational time for calculating trajectory of the quadcopter base is 43.9 microseconds, while the computational time for calculating the trajectory of the end effector is 25.7 microseconds. The goal of the aerial transport experiment is to grasp an object and put it on the target location. The aerial manipulator flying to the object, picking it up, and then flying to a target location to place the object there. The span time of the experiment is 88 seconds. The computational time for calculating the trajectory of the quadcopter is 45.6 microseconds, while the computational time for calculating the trajectory of the end effector is 32.8 microseconds. This experimental validates the effectiveness of the proposed method. Thank you for your interest in our research work.